Hi folks, this is the replacement lecture for Probability and Statistical Inference with Computing Sciences. This is going to cover sections 3.2 and 3.3 in our book. We're going to start talking about what a random variable is, and then the concept of expected value, variance, and standard deviation for discrete random variables. So if you go to the back of your book, this is basically starting around page 86 in the back of your book. So, as I said before, we're going to start this off with the concept of what's called a random variable. As far as the definition is concerned, a random variable which I'll abbreviate RV, is a function that maps each element or outcome in our sample space to a real number. So if you remember from covering functions, both in pre-calc and calculus, but as well as in discrete structures, we know that every function has got a domain. The domain, for our purpose, is the sample space. And you also talked about, in those classes, the concept of a codomain and a range. Codomains need not be unique. Okay, we can have a lot of different codomains. As far as the range is concerned, you can basically think about this as, for our purposes, the set of values to which the outcomes are mapped. In some cases, the codomain for a random variable will end up being the set of the one that we have to use is the set of real numbers, because there are times when a random variable can take on the value of any real number. But for many of our discrete random variables, in often cases, the range will typically be a subset of either the set of rational numbers or the set of integers. It need not be that way. As a matter of fact, one of the homework problems that you've got in section 3.3 involves a subset of the irrational numbers. But like I said, for a lot of the applications that we're going to do, and a lot of the applications that come up, quite often we're working with some subset of the rationals or the integers. So we'll start this off with a very simple example to give you the idea of what's going on here. The one we're going to start out with is the concept that we flip a coin 3 times. And quite often what's going to help, although it won't always be possible here, is to go ahead and write out the sample space. So let's say the sample space here, again, we're taking a look at flipping a coin 3 times. So one possibility is that we get 3 heads. Another possibility is that we get 2 heads followed by a tail, but we can also get 2 heads and a tail in the form HTH or THH. We can get 1 head and 2 tails, so that's head, tail, 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 head, tail, 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 head. And we can also get 3 tails. So, let's say that we've got a random variable x. Our random variables are denoted by uppercase letters. And let's define x to be the number of heads obtained in these 3 flips. So the possible values of x are 0, 1, 2, and 3. So we're going to summarize all of this in a little table here. You'll notice I have a lowercase x here. The lowercase corresponds to the values. The uppercase corresponds to the variable itself. Possibilities are 0, 1, 2, and 3. The next notation, lowercase p of x, stands for the probability that the random variable x, capital X, is equal to a specific value, little x. Now, for the purpose of this problem, what we're going to do is we're going to assume that the coin is evenly weighted. And if the coin is evenly weighted, then each outcome has probability 1/8. So in order to fill in the rest of this table, we basically need to count which outcomes correspond to the different values of x. So in the first case here, we have x equals 3. In each of the next 3 cases, we have x equals 2. The next 3, we have x equals 1. And in the last case, x equals 0. So since we only have one way to get x equals 0, the probability that x is 0 is 1/8. The probability that x equals 1, there are 3 ways that this can happen, so that's 3/8. The next one, there are 3 ways that x can be equal to 2, so that's 3/8. And in the last case, we have x equals 3. There's only one way that can happen, and so that's got probability 1/8. The table that we've got here summarizes what's called the probability mass function, or PMF. When we get to chapter 4, we'll actually have a formal definition as to why a variable is discrete versus why it's continuous. But we certainly did talk about discrete and continuous variables in terms of data, and at least for now, until we get to that formal definition, you can think about this the same way that you did back at the beginning of the semester when we were doing the introductory data analysis. There are some basic properties that go along with the probability properties we've talked about here. One of them is that the probability of x has to be greater than or equal to 0 for all x. And the second one, and this is for a discrete random variable, and again a carryover here, if we do the sum over all values of x, of p of x, this has to be 1. Nothing new about those properties, just applied here to a discrete random variable. Okay, so the next couple of examples we're going to look at are other ones where we're doing this type of thing. And we'll look at them out of the book. So these problems are on pages 90 and 91. The first problem that we're going to look at here is, there it is, it's number 3.3 on page 90. And what it says is the following. A group of 4 components is known to contain 2 defectives. An inspector tests the components one at a time until the 2 defectives are located. Once she locates the 2 defectives, she stops testing, but the second defective is tested to ensure accuracy. Let y denote the number of the test on which the second defective is found, and find the probability distribution, or the mass function for y. So we've got 4 components, 2 of which are defective. So one thing we know off the bat, in order to be able to find both, the smallest possible value of y is 2. It's also possible that we may have to go through all of the components, so the largest possible value is 4, and 3 is certainly possible in between. So there are a number of ways that we can do this. I'm going to demonstrate a couple of them here. In the case of the first part, where y equals 2, we're looking for p of 2. What has to happen here is for the first 2 items chosen to both be defective. So one way that we can do this, probability that the first 2 items are defective, we can use the combinatorial probability that we did in chapter 2. This is method 1. We have 4 items in our population. We're choosing 2 of them. As far as we're concerned, the population is split up into the defective and those that are not defective. We're told 2 are defective and 2 are non-defective. And if we're going to find the 2 that are defective on the first 2 picks, then this is going to be 2 choose 2, and we won't have chosen any of the non-defectives. 2 choose 2, of course, is 1, same with 2 choose 0. So this becomes 1, and 4 choose 2 works out to be 6. So the probability that y is equal to 2 is 1/6. As I said, there's another method that we can use where we're effectively using the multiplication rule and conditional probability. So if we're using method 2, what we're looking for is the probability that the first item is defective and the second item is defective. So this is going to be equal to the probability that the second item is defective, given that the first item is defective, times the probability that the first is defective. Well, the first one being defective, we've got 4 items, 2 of them are defective, so the second piece of this product is going to be 2 over 4. Now, the probability the second one is defective, given that the first one is defective, we're down to 3 items to choose from, and there's only 1 left that's defective, so we've got 1/3 times 2/4, and again, that's 1/6. show you both of these methods right now because for some other parts of this problem, it's going to be easier to use one method as opposed to the other. Now, move on to P of 3. For the probability that y equals 3, what has to happen in this case is that exactly one of the first two is defective, and the third is defective. So again, we're going to be using intersections here. We're going to use the multiplication rule for this. And again, we're working with conditional probabilities here. So if you want to think about this in terms of which one's conditional based on the other one, anytime you're doing something sequentially, you think about it from the standpoint of the latter piece being conditional on what happened before it. So P of 3 is going to be the probability that the third item is defective. Oops. Given that one of the first two is defective times the probability that one of the first two is defective. So we'll handle the conditional part first. We're down to 2 items, and if one of the first 2 is defective, we've chosen 2 items, we're down to 2 of them, we've picked one good one, one defective one, so we're left with one good one and one defective one. So the probability the third item is defective is going to be 1 over 2, the 2 corresponding to the 2 items left, the 1 corresponding to the 1 that's defective. Now, as far as one of the first 2 being defective, we can go back to our combinations the way we did before. We're looking at the first 2, so we have 4 choose 2. And again, we have our defectives and we have our non-defectives. There's 2 of each. And for one of the first 2 to be defective, we choose 1 from the defective group and 1 from the non-defective group. This becomes 1/2 times 2 times 2 divided by 6, and you get a third. And again, to demonstrate this method one more time for y equals 4, we'll go through the process. The thing is, when we're down to our last one, we should know what we should get here. The thing you have to worry about is whether you made any mistakes calculating these other probabilities, but this should be whatever's left. If you add these 2 together, you get a half. So our result, if we've done everything correctly, for P of 4 should be a half. So basically what we're looking at here for P of 4 is that exactly one of the first 3 is defective and the fourth is defective. So filling in what we have up here, we have the probability that the fourth item is defective, given that one of the first 3 is defective, times the probability that one of the first 3 is defective. I know I used whiteboard tricks, so if you haven't already stopped this to finish writing it in, I'll give you a moment. Okay, so as far as our conditional probability is concerned, we're down to one item, and there's only one defective left. So the probability the fourth item is defective, given that one of the first three is defective, has to be 1/1. As far as one of the first three being defective, we now have 4 choose 3 in the denominator. Again, we have our defectives and our non-defectives, 2 of each. We chose 1 defective, and we chose 2 non-defectives. 1/1 is 1, so we'll drop that out. 2 choose 1 is 2, 2 choose 2 is 1, 4 choose 3 is 4, and there's our half. Okay, the next one is 3.8 on this same page. .8 says the following. A single cell can either die with probability 0.1 or split into 2 cells with probability 0.9, producing a new generation of cells. Each cell in the new generation dies or splits into 2 cells independently with the same probabilities as the initial cell. Find the probability distribution for the number of cells in the next generation. So for this problem, it'll be a little bit easier to think about this one as a tree, using a tree diagram. So we're going to start off with our original cell. So we've got 1 cell at that point. The cell is either going to die or it's going to split, and both will survive. So if it dies, then we're down to 0 cells, and if it splits, we've got 2. In the next generation, each of these 2 cells can either die or split. So if both of them die, then we're down to 0 cells. If one dies and the other one splits, then we still have 2. And if both split successfully, we have 4. So X is going to be the number of cells after 2 generations. And what we can see here is that the values of X that are possible are 0, 2, and 4. So what we're told is the probability a cell dies is 0.1. So the probability that the first cell dies is 0.1. The probability that the cell splits successfully is 0.9. Now, for the next generation, we're told that the cells split or die independently of each other. So as far as an example here, the case we end up with 4, this is going to be the probability that the first new cell splits successfully. Intersected with the second new cell split successfully. told that the probability for each one of these is 0.9 and that these events are independent of each other. So because of that, we can take each one of these probabilities and multiply them. So we've got 0.9 squared, which is 0.81. Similarly, if we're going to end up with both cells dying, the probability corresponding to this is going to be 0.1 squared, 0.01. And in the case of ending up with 2 after the second generation, basically what we're looking at here is a set of 2 possibilities. The first splits and the second dies, or the first dies and the second splits. We know we've got independence that we can use as far as the intersections are concerned, but the bigger events connected by a union, like we said before, anytime we see a union, one of the first questions is, are the events mutually exclusive? Can the first cell split and the second one die at the same time that the first one dies and the second splits? Well, of course not. Can't happen. So we're going to take each of these probabilities and add them. So, the probability that the first one splits is 0.9. The probability that the second one dies is 0.1. In the second case, the probability that the first one dies is 0.1. The probability that the second one splits is 0.9. Each one of those is 0.09. So when we add them together, we get 0.18. Okay, so these probabilities right here, what you have to remember is these are the probabilities given that we're starting with 2 cells. So in order to get the probabilities corresponding to this, we're going to have to, as we did with the law of total probability, we're going to have to multiply each one of these probabilities by 0.9 because we're looking for the intersection of the events on each set of branches. So the probability that the first generation cell splits successfully and then the next 2 die is going to be 0.9 times 0.01. And so that's going to give us 0.009. In the second case, the probability that the first generation cell splits and then one of those 2 dies and the other one survives is going to be 0.9 times 0.18, which works out to be 0.162. And in the last case, the probability that the first generation cell splits successfully and both of the new ones split successfully will be 0.9 times 0.81. And that gives us 0.729. So, as far as we're concerned, the only way that we can end up with 4 cells after 2 generational splits is right here. And so the probability that x is 4 is 0.729. Similarly, here's the only way we end up with 2. So this probability is 0.162. The probability that we end up having 0 Well, we either have 0 because we had a successful split and then both of them died, or because the original one died to begin with. This is connected by a union, and so the probability of having no cells is going to be the sum of these, which is 0.109. And again, if you add those up, you will see that you get 1. Okay. Once you've got one of these tables, in some cases you need to calculate probabilities of events corresponding to the probabilities that are in these tables. So for the purpose of doing this, I'm going to take a table from a different part of the book. This table appears on page 98, and it's the table that's in problem 3.14. You've got 3.14 to do for homework, so I'm going to be asking or demonstrating something different than what's in that question. But let me put this table up here. So we've got y and p of y. The values of y go from 3 to 13. What we've got here, it says in this problem, is the maximum patent life for a new drug is 17 years. Subtracting the length of time required by the FDA for testing and approval of the drug provides the actual patent life for the drug. That is the length of time that the company has to recover research and development costs to make a profit. So those values up there are the number of years for the actual patent life associated with new drugs, and the corresponding probabilities are 0.03, 0.05, 0.07, 0.1, 0.14, 0.2, 0.18, 0.12, 0.07, 0.03, and 0.01. So let's say that what we had here is the question, what's the probability that the actual patent life is at least 9 years? Effectively, what we're asking here is the question, what's the probability that y is greater than or equal to 9? One of the nice things about a discrete random variable you're about to see as we write this out. In order for y to be greater than or equal to 9, when you think about this table, this is the probability that y equals 9, union, y equals 10, union, y equals 11, union, y equals 12, union, y equals 13. Remember, the unions are ors. So, again, we're connected by unions here, so we're going to ask the question, are these events pairwise mutually exclusive? Is it possible for y to equal 9 at the same time that y is equal to 10? No, that lifetime can't be both 9 and 10 years simultaneously. And what you end up having for any random variable here is that different values of the random variable correspond to pairwise mutually exclusive events. And so when we're doing this, in order to get this probability, you go back to the third axiom, all we have to do is add up the corresponding probabilities in this table. So in this case, we've got 0.18 plus 0.12 plus 0.07 plus 0.03 plus 0.01. If you add all of this up, you get 0.41. Similarly, if we were looking for the probability that 5 is less than or equal to y, which is less than 8, the corresponding values that are in here, well, we're not including 8, so we're really only using 5, 6, and 7. So this is the probability that y equals 5, plus the probability that y equals 6, plus the probability that y equals 7. That's going to be 0.07 plus 0.1 plus 0.14, and that probability is 0.31. So when you have the mass function like this, and you're asked to find one of these probabilities, essentially what you're going to be doing is adding together individual probabilities. One more example using this table. Let's say we're interested in the probability that y is greater than or equal to 11, given that y is greater than or equal to 9. So we're asking, what's the probability that the patent life is 11 or more years, given that it's 9 or more years? It's a conditional probability. We go right back to the definition in chapter 2. So this is the probability that y is greater than or equal to 11, intersected with the event y is greater than or equal to 9, divided by the probability that y is greater than or equal to 9. As far as our intersection is concerned, we have to have values of y that satisfy both of these. So any value of y has to be 11 or larger, and it also has to be 9 or larger. Well, a value such as 10 will satisfy y greater than or equal to 9, but it won't satisfy y greater than or equal to 11. So the intersection here is the event y is greater than or equal to 11. And here we have the probability that y is greater than or equal to 9. If we go back to our table here to get the probability that y is greater than or equal to 11, we're adding up our last three probabilities, 0.07, 0.03, and 0.01. And then we're going to divide by what we got for our first example, which was adding the last 5. We got 0.41. So this is 0.11 over 0.41. If you want, 11 over 41, which is going to be slightly more than a quarter.